Welcome to this video. My name is Mark Scythian. The date today is December 28th, 2024. And this video is going to prove that a typical electric vehicle full battery charge is equivalent to 1.9 gallons of gasoline. So electric vehicles use lithium-ion or lithium-polymerized-ion constant current batteries. So the typical current capacity is 30,000 milliamp hours. So that's just saying there's 30 amps for one continuous hour. And the average C discharge rate is there is a charge rate in coulombs and there's also a discharge rate in coulombs. So that typical across 2 to 5 C discharge is about 2.6. And so 111 cells times 3.6 volts per cell is the lithium polymer or lithium ion cell voltage capacity per cell, 3.3 to 4.2. So that's the charge to discharge equivalent of 3.6 volts per cell times 111 cells. So 400 volts, 111 cells, 30,000 mAh, 2.6 C average discharge. So that's a very typical electric vehicle battery metric standard. And again, this is not a high-end EV, this is not a low-end EV, but a typical electric vehicle that's most sold. So what this is saying is that we can draw 30 amps continuous constant current for one full hour at 30,000 mAh, milliamp hours. So if we were to multiply the amp hours rather than the milliamp hours times the C discharge rate, in this case the average current discharge at 2.6 C, 400 volts, 111 cells, 30,000 mAh translates to 78 amps. So with direct current electricity DC, we can simply multiply the voltage times the current to calculate the DC electrical power output. So in this case, 31,200 watts then flows to the AC power inverter, which converts the DC to AC. That's an AC electrical standard at 110 volts, RMS voltage at 60 cycles per second, 60 hertz. So the typical inverter conversion efficiency is about 85%. Some are 90%, but 85 is the average value of efficiency at the AC power inverters for electric vehicle applications. So this then converts the 31,200 watts of DC electrical power to 26,520 watts of AC true power, for which 4% is lost in the wiring. So we have AC electrical wiring efficiency of 96%. So the motor takes in 25,459.2 watts of AC true power, and then it multiplies itself times the AC electric motor's electromotive efficiency of 85%. So this then converts the AC true power into mechanical power, or a mechanical power output of 21,640.3 watts, for which we divide it into 746 to calculate the brake horsepower at the electric motor's output drive. And so then we can get an idea of the torque and RPM that occurs on such a motor. And so if we just take the 21,640.3 watts of mechanical power is also equal to 21,640.3 Newton meters per second of mechanical power. We can then multiply this times the radius of the output drive. So that's a 25 millimeter diameter. We convert the 25 millimeters to meters diameter and then divide it by 2 to get meters radius times 21,640.3 newtons. So this motor will have 270.2 Newton meters of torque. We divide the mechanical power output, the power, into the torque to get the angular velocity of 80.1 radians per second, then divide it by 2 pi radians per revolution. So that has an angular velocity of equivalent to 12.75 revolutions per second times 60 seconds, so 765.3 RPM. Then we divide the Newton meter torque value into foot pounds, 1.36 Newton meters to 1 foot pound, so 198.7 foot pounds torque at 765.3 RPM. That translates to 29 brake horsepower or 21,640.3 watts of mechanical power. So this is what we're dealing with in the average EV. And so that gives us a no load overall efficiency of 69.36%. And so this is first the no load metrics, as if the motor's taken out of the EV, placed on a stand, and then all of the parametric engineering calculations are made to understand the motor. This then takes us to the next slide, which is the internal combustion engine equivalent to the gasoline, or to the AC electric motor, the gasoline combustion equivalent. So again, we're going to apply 29 brake horsepower to the gasoline piston engine, a typical late model mid-size sedan with 4 cylinders, inline 4, 1.9 liters of displacement. So with gasoline piston engines, we have a brake thermal efficiency of 33% no load. So if we simply take the inverse of the brake thermal efficiency, 1 over 0.33, it will require 3 times more gasoline input equivalent to the brake horsepower output. So it will take an equivalent of 87.9 horsepower in the form of burning fuel. This should be IHP here, because the friction power lost to run the engine subtracted from the IHP yields the usable brake horsepower output. So we know this 29 brake horsepower at a gasoline piston engine is going to require 87.9 horsepower in the form of burning fuel. So we haven't converted it to mechanical power, we're just finding an equivalent. So if we multiply that times 746 watts to horsepower, that's equal to 65,573.4 watts in the form of burning fuel. Has not been converted to mechanical power yet. So now we want to know the heat that this burning fuel is discharging, absorbed through the engine, and that is then divided into 1056 watts is equal to 1 BTU per second of heat output, so 62.1 BTUs per second. We then divide this into the energy density of gasoline, which is 20,000 BTUs per pound. So this then calculates to 0.003105 pounds per second of gasoline consumption, then times 3,600 seconds to an hour. So this is 11.2 pounds per hour gasoline consumption, for which we then divide into the fuel density of gasoline, which is 6 pounds per 1 US gallon is the fuel density of gasoline. So 1.9 gallons of gasoline consumption over 1 hour is equal to the typical electric vehicle full battery charge driving at cruise conditions for 1 hour. And so we look at get an idea of the torque and RPM involved, the equivalent. This would then require an equivalent of 202.1 foot-pounds of torque at 750 RPM, and that is the 29 brake horsepower. Of course, based on the transmission system, we would then have a different type of a metric, closer to a higher RPM, but this is a base value, so what we gain in RPM, we drop in torque. So on an equivalent gasoline engine, you might have 1400 RPM and substantially lower torque, probably in the 150 range or lower, but the power value is identical. That's what really matters here. So the most relevant calculation is that one full battery charge on an EV is the same potential energy as 1.9 gallons of gasoline in a gasoline-powered automobile. So this takes us to the next slide here, which is more of an incidental calculation on understanding the duty cycle with respect to the cost. So if we drew all 30 amps at a full discharge C rating of 5, so 2 to 5 is the typical C discharge rating for lithium-ion batteries, and 2.6 is the average. So the high end is 5. So this would be 5 times 30, and then we have 150 amps times 400 volts, and that's 60,000 amps or 60 kilowatts times 110. So that's actually $6,660 for the battery. But because we're at about a 50% duty cycle, $3,463.2 of $6,660, it's then validated that the average use cycling rate of an EV battery is a duty cycle of about 52%. We'll just say 50% duty cycle. And so then it is a required wait time, and a typical EV charger for residential applications is about 120 volts AC pushing 15 amps at a power factor of 1. So that's 1.8 kilowatt hours times 10 hours charge time at 15 cents a kilowatt hour, and 18 kilowatt hours, the charge cost is negligible at just $2.70 per charge. However, the wait time may not be time effective, while the charge cost is cost effective. However, we know in a matter of seconds we could charge the same potential energy into the gasoline automobile's fuel tank, equal to 1.9 gallons, so probably just 20 seconds of fill time, and a cost of $5.78. So definitely the gasoline is time effective. So now we have to take these two powertrain devices, the electric motor and the gasoline combustion engine, and place them into the vehicles, and now do the load condition, runtime, and range analysis. So we'll take the average values for vehicle weight, and again, this is mid-size sedan, 4-door. The weights are relatively equal across both the GV and the EV, as well as the average aerodynamic drag coefficient, the vehicle projected frontal area, or the vehicle's projected frontal area, average air density. We'll use the slugs per cubic foot. I missed the cube symbol here. And then average highway speed. Again, this is a conservative calculation. Maybe 1 out of 3 motorists are driving on the right lane on U.S. highways at 70 miles per hour cruise control setting, but we'll use that as a highway metric of 70 miles per hour cruise. And so we don't have the acceleration, we have constant velocity, but we do have fluctuating accelerations across the hills and valleys and the curvature of the road. So that's going to require a bit more power loss other than the aerodynamic drag and the tire rolling resistance that opposes the inertia of the vehicle. Hence, that will be a power to keep the vehicle at constant speed, which is considerably lower compared to acceleration, but it's somewhat subtle for constant speed maintenance. And then lastly, we have the tire rolling resistance, or the automobile/light truck tire rolling resistance coefficient. This is applicable to automobiles and light trucks under 8,000 pounds on dry paved road. And so that is a TRC, tire rolling coefficient, of 0.012. Now with trucks, semi-trucks, big trucks, that value will go up. It will increase to 0.018, 0.020, etc. And very giant semi-trucks can be as high as 0.025. So now we have the only forces opposing the inertia of the vehicle, the aerodynamic drag, and the tire rolling resistance. So we use these equations to calculate the power loss to overcome aerodynamic drag and tire rolling resistance. So when we do the calculations, it will require an additional 20 horsepower to keep the engine running, but we already have the brake horsepower standard of 29 bhp. So instead of subtracting from that value, we divide the 19.55 bhp load into the 29 bhp no load. So this calculates a coefficient of power draw of 0.67 at 70 miles per hour cruise highway conditions. So now we have a metric to go by, a coefficient of power draw of 0.67. Finding its reciprocal or inverse, we can then scale up the runtime to 1.49 hours rather than 1 hour. However, this is a theoretical calculation, as is the theoretical range. 70 miles per hour for 1.49 hours is 104.3 miles range theoretical. But then when we factor in the fluctuating acceleration coefficient of 0.6, this includes not just overcoming hills, but also curves, getting some of that power back on valleys. And then we have the wheel slips, the anti-skid systems that are subtly working. So when we add all these up, these on-off switches, and also the not perfectly linear roads, we actually lose about 38-39% over 1 hour, not in the short time of 5 or 10 minutes. So it's a subtle increase in power loss, but it levels out to about 0.6. So then we take the 104.3 mile range theoretical calculations, multiply it times 0.6. So our actual mileage range per EV charge is 62.6 miles, and that is if the vehicle does not have a gasoline piston engine driving a generator to then AC generator to then power the AC motor, which most EVs do. But if you have an EV that just solely relies on the battery charge, then you'll get between 60 and 70 miles of range on the latest model of a typical EV. Now we also have to factor in the power recovery circuits, and those are not with respect to regenerative braking, because that involves slowing the car down. We can't draw any power from the rotating wheels because the energy is conserved. The kinetic energy is having a maximum value without efficiency losses equal to the potential energy on board. So we can't just hook some piece of equipment up to the rotating wheels and draw any power out of that, because then we lose our overall power value. It transfers from the source to something else. But however, there are numerous brushless rotors and stators across the vehicle's accessories, and there's also the electronic software power conserving algorithms on board, which do partially shut down primary systems, keeping only the secondary during durations of constant speed. So when we add all this up, we actually do get a 10% power recovery dynamic without respect to braking, but with respect to constant velocity or speed on the highway. So we could take the 62.6, multiply it times 1.1, which is adding the 10% to the value, and this takes it up to about 68.9 miles. So approximately 70 miles to a charge on a typical EV. Now if we compare the same value to 29 brake horsepower, taking 19.55 out of it at a power draw coefficient of 0.67, it's reciprocal. We also do get 1.49 hours runtime, and we calculated already it's 1.9 gallons of gasoline equivalent to one full battery EV charge. And again, the range is 104.3 miles, a theoretical calculation. but we also have to factor in the FAC, the fluctuating acceleration coefficient of 0.6. And so if we were to just take the mileage for the combustion, that would be an actual value, so hence the theoretical is not written here. But when we want to actually get the MPG with respect to the losses of the FAC, fluctuating acceleration coefficient, is relevant to the MPG fuel economy. So then it brings down this theoretical 55 MPG to about 33, which is a real world calculation with respect to the mid-size sedans under 4,000 pounds at a constant speed of 70 miles per hour, cruise control. Again, it's not typical to see that on the highway, but there are at least 1 out of 3 motorists to stay in the right lane and set their cruise control at 70. And most highways are now, or freeways are like 80 miles per hour. So again, it is a conservative sticker value constant speed of 70. So you may have to slow down a little bit and speed up. However, you get credit for the average speed. So we'll say 70 miles per hour at 1.9 gallons of gasoline consumption over 1.49 hours, and then a fluctuating acceleration coefficient of 0.6. So those will report I acquired 33 miles per gallon, and that's what motorists will tell you. So this is where the value comes from the FAC, the subtle fluctuations in acceleration across a not perfectly linear road. So then we have an average gasoline fuel tank capacity on cars of about 14 gallons. So this translates practically to a gasoline vehicle maximum range average of 461 miles of range. So the final conclusion based on all the proofs is that a typical electric vehicle full battery charge is equivalent to 1.9 gallons of gasoline as an equivalent potential energy match, i.e. the battery charge potential energy to the chemical potential energy of gasoline. One full battery charge of an EV is equivalent to the potential energy of 1.9 gallons of gasoline. Thank you for watching this video and have a great day.